Bismillahirrahmanirrahim. Assalamu alaikum, dear students. How are you? I hope you will be fine. I am your chemistry teacher of class 10th. Lecture number 7. Dear students, in today's lecture, we are going to study the following topics: the law of mass action, derivation of equilibrium constant with the help of law of mass action, and derivation of equilibrium constant Kc for a general reaction. Our first topic is law of mass action. Gilbert and Weig in 1869 put forward this law. According to this law, the rate at which a substance reacts is directly proportional to its active mass, and the rate of reaction is directly proportional to the product of the active masses of reacting substances. Dear students, this law is very simple to understand. There is a direct relationship between rate of reaction and active masses of reacting substances. The law has the two portions. In first one, the rate at which a substance react. We are talking about a single unit. We are talking about a single substance. The rate at which a substance reacts is directly proportional to its active mass. And in the second part, the rate of reaction is directly proportional to the product of active masses of all the reacting substances. The term active mass means molar concentration of the substances, amount of the reacting substances. Value of the concentration of a substances means active mass. For example, if a product have 50 moles per dm cube in a reaction, which means that 50 moles per dm cube is an active mass of that substance. Now, dear students, let's move forward towards the derivation of equilibrium constant Kc. For example, consider a reversible reaction in which reactants A and B combines to form the product C and D. Dear students, we have to keep in mind that this reaction is a reversible reaction. In this reaction, reactants A and B combines to form the product C and D. Suppose A square brackets, B square brackets, C and D square brackets are the molar concentration of A, reactant A, B, product C and product D respectively. Dear students, a double arrow shows that this reaction is a reversible reaction, and a reversible reaction can only be possible in a closed system. Here is a diagram in which you can see that in a reversible reaction, reactants combine to form products. This is a forward reaction. And products again recombine into reactant. This is a reverse reaction. And in a reversible reaction, both of the forward and reverse reaction take place simultaneously. Reactant are converted into products and product are converting back into reactants. Dear students, in the start of a reversible reaction, initial stages, as we studied in the previous lecture in characteristics of forward reaction, at initial state the rate of forward reaction is fast. So, according to law of mass action, the rate of forward reaction is directly proportional to the A and B's active masses, which is Rf directly proportional to A and B. To remove the proportional sign, we add constant of proportionality, so Rf is equal to Kf, that is forward reaction constant, and A into B active masses. So Rf is equal to Kf, active masses of A and active mass of B. This is the rate of forward reaction equation. Similarly, when reaction proceeds, after some time, reverse reaction also started. So the equation is the rate of reverse reaction proportional to active masses of C and D. So R are proportional to C and D active masses. So to remove the proportionality sign, we include Kr, that is constant of reverse reaction. So Rr is equal to Kr and active masses of C and D. So Rr is equal to Kr and active masses of C and D. And now dear students, writing them in a comparison way, then rate of forward reaction is directly proportional to the active masses of A and B, and rate of reverse reaction directly proportional to the molar concentration of C and D. So Rf is equal to Kfa and B, and Rr is equal to Kr C and D. A, B, C, D are molar concentration. So when molar concentration increases, the rate of reaction is also increases because both are directly proportional to each other. If we increase the molar concentration of reactant or the product, the rate of reaction also increases because they are in direct relation or directly proportional to each other. And after that, in a reversible reaction, after some time, a stage reaches at which equilibrium happens. So at the equilibrium, rate of forward reaction becomes equal to the rate of reverse reaction. So adding of these equations, Rf is equal to Kfa into B and Rr is equal to Krc into D. Then we get Kf over Kr and C over D over A and B. Dear students, you can see in the equation that constant of forward reaction and constant of reverse reaction are in the form of a ratio, that is Kf over Kr, and active masses of products, which is equal to active masses of products over the active masses of reactant. So the ratio of forward constant and reverse constant is equal to equilibrium constant, that is equal to Kc. So Kc is equal to active masses of product C and D over active masses of reactant. So Kc is a ratio of active masses of product and active masses of reactant, which is called Kc equilibrium constant expression. Now dear students, let us apply the law of mass action for a general reaction and derivation of expression for equilibrium constant for general reaction. Here is another reversible reaction, and difference between the previous is that the small a, small b and small c and small d. Small a means number of moles or coefficient. For example, 5a means 5 moles of A. So small a means any number, small b means any number, small c means any number, and small d means any number. So 5, you can see that, for example, 5a plus 3b is equal to 2c plus 3d, which means that small a, small b, small c and small d are number of moles in a chemical equation. And we can define the law of mass action in another way, that rate of chemical reaction is directly proportional to the multiplication of or product of all the molar concentration of its reactants, and raised to the power means the number of small a and small b becomes their power, and which means that active masses gets a power on it, which means number of moles of a reactant. You can see in the next picture. So there is a difference between the previous one, that the active mass A has a small a on it, the active mass B has small b and small c and small d, which are the number of moles, which means if 5a means active mass A raised to the power 5 or B raised to the power 5. So A, B, C and D are the molar concentration of mole per dm cube of A and B and C and D respectively. Dear students, you should keep in mind that both of the examples or derivations are the same, with a slight difference of the raised to the power A, B and C. So this derivation is very much similar to the last one, which was simple, and it is some more extra in it, which are small a, b and c molar concentrations. So according to law of mass action, the rate of forward reaction is directly proportional to AABB, and which is RF is equal to KF, which is forward reaction constant as we studied earlier. And similarly, rate of reverse reaction is equal to RR is equal to KR CCDD. And rate of forward reaction, it is written in comparison, and at equilibrium, rate of forward reaction becomes equal to rate of reverse reaction. Similarly, with the previous one, we derived the Kc equilibrium constant expression, which is ratio of forward constant and reverse reaction constant. So dear students, to proper understanding and better learning, you have to watch this video. You have to watch this video in few pauses and steps. Then you will understand it better. It's a very simple law. Practice it with mathematical form twice or thrice, then you will learn it by heart. Dear students, it's over for today. In the end of this lecture, I have an assignment for you to learn and practice. State this law of mass action, derive the equilibrium constant expression for a general reaction, and a simple question is how the active mass is represented. So active mass is represented by square brackets. Stay home, be safe. Thank you very much, students. Allah Hafiz.